other day. So if you could take those out, please. We're going to finish up our chapter 14 notes today. I will be posting grades probably 7th hour today, so you guys know, in case you have issues with eligibility for sports or something of that nature coming up. Make sure you have everything in. All right, we're going to talk about the solvation process here. That's where the solute particles are going to surround the solvent particles. In water, we call that hydration. And we have an attraction between the dipoles of the water molecule and the ions of the crystal are greater. And we talked about that a little while ago. I also made a supersaturated solution for you guys so you can see that. I'm going to try to get this cooled off enough to get it to work. And then we had talked about this thixotrophic material the other day. We were talking about clay, and we were talking about earthquakes and different things like that, and how the clay can change you know, the issues with engineering and foundations for houses and stuff like that. So I got a thixotrophic solution mixed up here. I'm going to pass that around to you guys here in a minute to try to get this super saturated solution cooled off enough to be able to do that demo for you as well. So this is the super saturated solution. It's sodium acetate, and you can see that it looks just like water right now. Okay, but it's super saturated, meaning that it has a lot of solute. For those of you playing at home, this is what it looks like. A lot of solute dissolved in here. And for those B-Day folks that are watching this at home, I'll do this for you when you come in on Monday. If we agitate this, sometimes they can really agitate it and get it to go into precipitate out. Like if we had an earthquake. So if you had a house built on one of these like clay, okay, or no, that's that other one. Never mind, that's a different one. This is the precipitate. I'm getting my stuff confused now. So this is the precipitate. I don't know if I'm going to be able to get angry enough by shaking this. So I'm going to add one of those seed crystals. If you remember, I talked to you guys about the seed crystal. And if we add just a seed crystal into here, where did my hair is? So I'm going to hold that up so you can see it all. Sometimes this happens pretty quick. Sometimes other times it doesn't. Yeah, there we go. See how just the seed crystals, see how that's starting to come out of, precipitate out? I just added those couple little crystals in there. That's all it took. And now I'm going to put it back on here, and we'll get it to go back into solution. This is that thixotrophic thing. So if you turn the beaker, you'll see that it flows like a liquid, kind of wild. And you guys can play with this a little bit when I pass it around. But if you take this guy, stab it, and it feels like a solid. And this is the stuff that I was talking about, how if they built like a house on something like this, like clay, and you had an earthquake come along, it's going to flow like a liquid. And then your foundation of your house is just going to be gone. You know, so in earthquake zones, you got to be real careful about the soil. So it's fun. It's kind of fun to play. I know. Congratulations. I'll have to go. Teacher Appreciation Week, they got all these gift cards to different places, and she put her name in for a drawing, and I won one of them, which I never win anything. But hey, the Megabucks lottery is tonight, so maybe I'll win that. If I'm not in school next week, you know what? Mega Millions or whatever it's called. Maybe it's my lucky day. All right, so when we talked about this the other day, this just kind of goes back to this slide that I was talking about. Here it is. So when we have these guys that are coming together, we've got a positive ions, we got negative ions, and they are, you see how that's back out of already. Back in the solution. Yeah. Just a little bit of heat will change that. All right. I wanted to pull that off of there so it has time to cool between now and 8th hour. So when you have this situation where you've got negative ion, positive ion, you've got these ionic solids, the attraction for the water is going to be greater than the attraction for each of these to one another. In situations where these guys attract more than the water attracts them, then it's going to be insoluble. And if you think back to that chart that I gave you a while back, where you had the N's and the S's, remember that? You had to bring them together. The ones with the N's, these positive and negative ions were more attracted to one another than they are to the water. And so it's insoluble. It stays together as a chunk, as a solid. Okay? And we talked, I got to go back to where we're at now. It's just a good diagram for showing that. All right, there we go. So during this process, okay, during the solvation process, the solute particles have to separate. That requires energy to pull those apart. The water molecules have to separate from one another because remember they're attracted to each other by the IMFs. So they've got to separate and allow for that ion to come in there. Both of those things take energy. And then when they come back together and they surround that ion, the water molecules surround the ion, that gives off energy. If it gives off more energy than it takes to pull them apart, it's an exothermic reaction, and it'll actually feel warm when you're bringing those two things together. So when I dilute down acids in the hood, okay, I always do it in the hood because it gives off a lot of heat and it gives off a really bad smell that makes me feel really icky and cough and like, whoa, hello, wake up. So I always do those in the hood, but it does give off a lot of heat. When I'm diluting down like sulfuric acid, which is super high molarity, it's like 18 molar, really concentrated. I actually have to do that in an ice bath because I have a potential of giving off so much heat that will actually crack my glassware. And if you think way back to your safety contract, back in the beginning of the year, one of the things on your safety contract was that you always add acid to water instead of water to acid, because it gives us so much heat in that process that if you add that acid to the water is able to absorb that heat difference. But if you do it the other way around, there's so much heat given off that you could actually cause like problems like broken glassware, and you know, then you've got acid on you, which can eat holes in you and your clothes and everything else. So so yeah, there's actually a lot of heat given off in this process. All right, things that affect solvation, stirring, and these are like practical things for like in your kitchen, sort of, so to speak. Like if you want to make something come together faster, you stir it, right? I mean, it just makes sense. You're making it go into solution faster. Increase the surface area. If you want something to happen faster, you break it up into pieces and it goes faster because the surface area increases. And you guys probably did like a surface area to volume lab in biology last year, or whenever you took biology, where you looked at the surface area of a cell versus like osmosis and diffusion and that sort of thing, and how if you have a bigger cell, you've got less surface area by volume compared to the volume. Remember doing something like that? They probably did it with like agar, or I don't know, they do it with different things. So I always did one where they had to cut out cubes and then fill it with rice and do calculations with that. Temperature. Temperature is a real important one. We're going to talk about that in terms of solids and in terms of gases. So with solids, if you increase the temperature, the solid will go into solution better. And if you've ever worked with like trying to get like sugar to dissolve in water, okay, if you heat it up, it'll dissolve and you'll get more sugar dissolved in there than you would otherwise. So if you want to make like super syrupy Kool-Aid, heat your water up, you can mix more than just a cup of sugar in with it. You can mix more, it'll go into solution, and then cool it down and you can drink it. You need your sugar rush for some reason. Gases, however, are just the opposite. As the temperature increases, the amount of gas that can be dissolved in that solution decreases. So your soda pop, for example, has gas dissolved in it, okay? Soda tastes better cold. One of the reasons why it tastes better cold is because it has more fizz in it. The warmer your pop is when you open it, the more carbon dioxide is going to come out of solution. So it'll be flatter much faster if it's that way. Now, your pop is also under pressure. So if you increase the pressure, you can dissolve more gas in that water as well. And that's why they put pop under pressure. So when you open it up, it goes, or pop the thing or whatever. It's under pressure in there because that keeps the gas dissolved in that solution. You actually have gas dissolved in the synovial fluid around your joints. Okay? And if you decrease the pressure on your joint by opening it up, that gas will actually come out of solution. And that's what you hear when you hear a pop, when you pop your joints. What you're hearing is actually synovial fluid, the gas coming out of that synovial fluid. Now that gas is still in there, so you give it a few minutes under pressure, and that gas will go back into solution, and then a little bit later you can pop your finger again, or whatever joint it is. I'm not telling you to go pop your fingers or joints. If your parents have said not to do this because it makes things bad, don't do it. Don't get Lippy in trouble. I'm not going to weigh in on how I feel about it one way or the other, but if your parents told you not to do it, don't do it. My little disclaimer. All right. Solubility depends on the nature of the solvent and the solute. And unsaturated solutions, we have solutions that contain less dissolved solute for a given temperature. I gotta get Miss Hanson some money. She's buying me GRs today. Well, she's not buying me, but she's. Do I have a 10? There's a 10. I should cover it all. That should easily cover it. It's $8.50 plus tax in my part of the delivery fee. Yum! Yum, yum, yum. Love me some GRs. Haven't had GRs in probably a year. Huh? My friend loves some GRs. Chicken artichoke panini with extra mayo. All right. Saturated solution then has more solute dissolved than can be handled.
There's a lot of things I don't like. Tomatoes. I don't like ketchup. I like tomato sauce. I like tomatoes like
A good BLT with mayo. Oh my god. There's very little as good as that. All right, so solubility. Generally speaking, solids will increase their solubility as we increase the temperature. And if we had more time, I actually have you guys do a lab where you see this happening. That's one of the labs that I had this year. So, sorry. Again, supersaturated is going to contain more dissolved solute than a saturated at the same temperature. To form it, you heat it up. So that's why I heated it up. And then I slowly cool it down. So it's going to cool down over time. And then that's going to be unstable. So if I add another couple crystals in there, it's going to pop back out again. Okay. So by 8th hour, it'll be cool enough. And then I'll be able to to do that demo again by 8th hour. So. All right, again, gases are less soluble in liquid solvents at high temperature unless we increase that pressure. And that's why they put POP under pressure, is to keep that in solution. Now, the other thing is that this pertains, these gases, as high temperature goes up, the gas dissolved in there decreases. That pertains to fish kills. So a lot of times during the summer, the temperatures will get so hot in the area that the fish that live in there don't have enough dissolved oxygen in the water, and they actually suffocate in the water and die. And if you own like an aquarium, for example, you have to keep that aquarium at a certain temperature. You know, it has to be warm enough for the fish, but it also can't get too hot, because if you get it too hot, you won't have enough dissolved oxygen in there, and they'll end up dying from that. So it's just something that you kind of have to be aware of. And that's Henry's law. We talked about that in terms of the solubility and the pressure. And if you decrease the pressure, then not as much gas can be dissolved in there. Okay, good? Makes sense? All right, so for those of you who gave me your 14-1 on time, I'll give that one back to you, and you can work on your homework. For the rest of you, I got that sheet run off again, and you can work on your homework on that. So let me stop sharing this and stop the recording so I can get this uploaded for the guys at home.